Good afternoon, everyone. Welcome to SNIA webinar series. Today we have Binita and Shubhankar to talk about fine-tuning large language models. Both of them have about 8 years of experience in Dell and system administration domain. Binita is also responsible for prioritizing features, analyzing and driving improvements to the process and various projects to get high quality. She's passionate about data mining and search engines. She's also a core member of Women in Action and NGO activist. Well, Shubhankar is also worked on HPC computing framework, CRM and automation. He's very passionate about innovation and application of AI. So we all look forward to a great webinar today and learning a lot about fine-tuning language models. Go ahead, Shubhankar.
Thank you, Kalyan, for the introduction. A very good day to all of you. Today, we will be presenting on the topic fine-tuning large language models, empowering AI for specialized application. So let's quickly see what do we have for today's agenda. So we'll start with the W's of large language models, like what is large language model, the evolution of large language models, who is a consumer of large language models. Then we'll give a brief introduction about Hugging Face. It's a platform for AI/ML enthusiasts. Then we'll go what is fine-tuning, what are the different processes that is involved in fine-tuning large language models. We will discuss briefly about two techniques, that is PEFT and RAG, which are a subset of different ways you can fine-tune your large language models, followed by challenges and opportunities. And we'll open for Q&A. So let's see what is the evolution of large language models first, before deep diving what exactly large language model. So it all started in the 1967 with ELIZA. So it was the first ever chatbot that was created, which was a simple rule-based chatbot. It doesn't understand the context of what the user is, the sentence that the user has inputted. Whatever the input the user gave, it actually gives back it as a form of question. So that's all it used to be. And in the late 1980s, right? If you see in 1988, the emergence of recurrent neural network started. So recurrent neural network was deeply inspired by the human brain and how it interconnects with the neurons. And the good point here is if ELIZA did not understand the context, here it was able to understand the context a bit more. But the only thing is, the limitation was it couldn't understand what are the long sentences and when there are long sentences, how these words are interconnected with each other. But RNN was the one which actually provided foundation for NLP. Then came, as I said, right, because the recurrent neural network had the issue of retaining the context of long sentences, that gave the foundation for long short-term memory, or LSTM. Whatever is the limitation of RNN, right, that was the advantage of LSTM. So it could actually keep track of long sentences, understand the context, could memorize the info. So RNN was famous, but LSTM could actually cover a lot of limitation that RNN couldn't. Then in the 2017, with the paper that was published in 2017, that is Attention is All You Need. That was actually the biggest milestone in AI/ML world, where, the transformer architecture came into picture, which was purely based on attention mechanism. So if you see, right, at its core, it was composed of encoders and decoders, and it was stacked with the feed-forward neural networks and self-attention. But the greatest advantage of transformer model was it could actually, parallelly, it could understand the models that it was trained on, and it could understand the context. So, the larger context was memorized, and it is the one which actually laid foundation to the big giants like Google Bird, ChatGPT, and anything which you are right now using. And ever since that, right, there has been a plethora of options of, generative AI and LLM mechanisms that is available. And I'm sure that all of you would have at least had tried once, like what is ChatGPT or what is Google Bard about. So if you see, this is something which has happened that ended up in the evolution of large language models. Now, before we deep dive into what is LLM, first we need to understand what is a language model. So language model is a type of artificial intelligence model that is trained on large amount of text data to understand and generate human-like language. Now, where do you exactly use this? If you see, right, in day-to-day example, we use it for, language translation. We use it for text generation. We use it for, image classification, sentiment analysis. There are a lot of tasks which a language model can do. This is also designed to predict the probability of a word sequence, but because it's related tightly coupled with language, it's more used for predicting the probability of a sequence of words or characters given the context of the previous word. So basically, just like how humans interacted, we memorize, we keep track of things. In a similar way, language model also keep track of things. Also, it understands the context of different words with respect to a different sentence that is being used. Like, let's say I train my model, right? And with whatever is currently available. And if I say apple is a dash, what is apple? So, by default, it gives a fruit because apple is generally, and it depends. Let's say if I'm not, tuning, if I'm not training my model with the generic training data, I can fine tune it in such a way that, it will end up saying that apple is a, big company or something else. It can, depending upon the context on which you are being trained your model. Also, it helps in learning the statistical relationship between words and the context in which they appear. So that is in general what a language model is. But when you come to large language model, right, that word itself, we should stress on the word large. We are talking about billions and even trillions of words and allowing them to capture a deeper understanding of language nuances and contextual dependencies. Now, these models are designed to understand and generate human-like text, just like our language model. Also, generate coherent and contextually relevant responses. Now, large language models are typically built using deep learning techniques like whatever we discussed so far, such as transformer architecture, which allow them to capture complex patterns and dependencies in the language. It is also noteworthy that, the term large is relative and can change over the time as new models with even great capabilities are developed. So now let's see in a high level what exactly as a training process of involved in large language model, right? So what is the basic thing that you need is definitely data. So it all starts with your data collection. And when I say data, there are a lot of unwanted things in that, like stop words, comma, uh, word, why, these type of words, right? So you pre-process all the data and you have now quite sanitized data. Then you go for tokenization of that data where you actually, split it in simple words. Then we have an architecture selection, like, whichever model, whichever architecture you want, whether it is transformer or if it's anything else, you have to choose your architecture. Then there is a training process involved. Then there is a hyper tuning, a hyperparameter tuning that is involved, regularization, optimization, and the last step is validation and evaluation. But it doesn't stop here. And we will be, discussing this whole process much in detail when we actually talk about fine tuning in the upcoming slides. So I'm just giving a brief overview of like what exactly this is. So when I say about, as I said, right, it doesn't stop at validation and evaluation. That is just a pit stop where you are going to check how what are the parameters you have taken, the model you have taken. Is it really good for your domain or your business? So this process will keep happening until you find that balance that okay, I'm getting a good, I have a good training data, and whatever output I'm getting is also valid in this particular use case. Now, where do we use or who are the consumers of this large language model? The first is customer experience and support, which we all know, right? A lot of people have now already using virtual assistants and enriched customer experience where, we apply the principle of sentiment analysis to figure out if a product is launched in the market, how is a customers, accepting it, what are the things that they are not really liking or liking about the product. So all these things can be done by large language model. Other one is social media, where content generation. Basically, you can write blogs, you can write articles. So all these things related to social media can be taken care of. Healthcare, where any medical diagnosis, you can just feed your LLM with data that is purely dependent with healthcare, and that will train it, and you can use it for your medical diagnosis purpose. Finance, marketing, and advertising, all these are where you have a target marketing depending upon the geography, demography of the user. You can push different marketing techniques and products to the people in that particular region. So these are the well-known use cases of LLM. Okay, now training small versus large language models. We just talk about the key differences with that, right? So as the name itself suggests, small versus large. Small means the data requirements are very less, with several thousands to few million data points is what is there. But when we talk about large, right, we have already spoke, it can be billions and trillions of data points that we are talking about. Now, the data, when the data is small, what is it that we associate it with, when it comes to training? There is definitely a need for computational resource, storage capacity, and the training time. Okay, so with respect to small, you need basically simple hardware setups like personal computers, or maybe small server clusters. Whereas in large language model, you need powerful GPUs and DPUs to access access to high performance computing cluster. In case of storage capacities, obviously small language models will need only minimum storage requirements, but whereas LLM will require a high capacity storage systems or distributed storage solutions to handle this huge amount of data. The training time required for small language models is from few hours to few days, but for LLM it takes days, weeks, or even months, depending upon your computational resources and training techniques that you are being used. Okay, so I hope now you have an overall idea about what exactly is a large language model, and what are the just an overview of like what exactly happens, right? Now, if you really want your hands to get dirty and figure out like what exactly is this LLM, this is a perfect platform. So Hugging Face is, again, it's an open source platform. It's a machine learning and data science platform and community that help users build, train, and deploy machine learning models. So, like I said, right, generally we work in GitHub, right? This is exactly like a GitHub for AI/ML enthusiast. So, what all you can do here? So, starting with, you can implement different machine language models. You can not only implement, you can share it so that the other users can consume it and discover other models that you have made, and also give feedback to you that okay, this is cool or this is not working really good. You can share and discover the data sets that you have used for training your model. You can fine tune your model, host demos, research, do any sort of research, right? Especially people who are in the research field, they need a lot of data. They need to know what are the different models that is available. So starting all these things from scratch is definitely going to be very time consuming. So this is a perfect place they can go. They can actually learn, do research, and figure out which is the best, set of whatever that whole process we were talking about, right? So they can basically conclude, okay, this particular domain, these are the best practices that we can follow. Also, it helps you in evaluating your ML models. All these are like closely related, right? You know, hosting a demo, doing your research activity, evaluating the ML models, and also getting feedback at the same time. Now, there are mainly three features that Hugging Face offers. One is model. So it hosts a large library of models that the user can filter by type, like what is trending, what is the most relevant one, what is the most downloaded ones. So based on that, you have a plethora of options of models and data sets. Data sets as we need, right? If we want to train any model, we need to have data for that. And for that, this is the best place to go. Spaces is like like the word itself, it's like your own space where you can build, deploy, and share machine learning demo apps. So this is how the Hugging Face, when if you just go and search, looks like. So if you see here, right, it allows you that what exactly is the task that you're looking at. Is it like feature extraction, or is it anything related to computer vision, or is it related to natural language processing like question answering or translation? So you can pick which is the task you want, and then you can pick models. So if you see here, we are talking about Sapphire model, and the domain is about text generation. Then there is Llama 2, whichever is the famous ones, right? You can actually go and you can see that, okay, people have also, this is the number of downloads, these many people have approved, they loved this particular model. So this is a go-to place where you can actually go, and it has a plenty of documentation, and a lot of people are using it currently. So please feel free to go here and just have an overview of like what exactly you can explore in Hugging Face. Okay, so over to you, Shubhankar.
Okay. So thanks, Punita. Good afternoon, everyone. Hope I'm audible, right?
Yes.
Okay. Yeah. So I hope that now we have a good context of what is basically a language model, what is a large language model, the difference behind that, and the use case also, right? So now what we'll start with is basically how we can use that Hugging Face models, basically the existing model that we call a pre-trained model. So as the name suggests, right, any pre-trained LLM models are basically mostly they're already trained, and they are trained by some research institutes, and those are trained on huge amount of data, and these models basically understands the basic grammar or basic context of the language. So these models are not specific for any particular task, but they are good at understanding the basic context, the basic grammar, right? And how we can use them? Okay, some of the popular pre-trained model can be like BART or GPT or Roberta. So these are some popular pre-trained models, right? Now, how we can use those models? Now, to use those models, this transformers library provides basically a pipeline concepts. Okay, now what is a pipeline? Now, pipeline is kind of an abstraction, okay, which contains a model. Uh, Sometimes it's a pre-trained model along with the provision to pre-process and post-processing of that model requirement, right? So whenever you're working model, we need some pre-processing and post-processing, right? So all these tasks are basically encapsulated within a pipeline, right? So that as a user, when someone is using this model, his task is actually very low. He can easily pull a model using pipeline and use that. So here are a few examples. We'll try to understand how this happens, right? In the first example, as you can see, right, we are basically importing pipeline from transformers, and then in the next line we are generating a model. Basically, we are defining a model, right? And there we are defining that we need a text generation model, right? So we're mentioning text generation, and as an optional, we can mention a model like distill GPT-2, or that is optional, right? In that case, pipeline will decide a model. So we can mention the task only. So once we have the model, you can see in the next line, we can basically now use the model. We can basically ask questions, right? Here, this is a text generation. So obviously it will, the expectation is that it will generate some text for me. So given some text, for example, in this course, we will teach you how to, this is the initial line suppose we are providing, and we are asking that to generate suppose 30 next words, right? And the number of minimum sequence to, basically we want two such type of answers, right? So given this, right, it can actually now give me an output, right? As you can see in below, we have it has basically completed the sentence. It has generated the text for us. Or the next model, that is called a mask model. So in the mask model, what we necessarily do is basically to fill a sentence, right? There is some missing word, and it has to guess the word. And this mask model is also very basic concept of how any pre-trained model are trained. Like we're mainly considering the textual data here. Okay, we are only talking about textual data here. So in training the pre-trained model, right? So huge amount of data is taken, and there are some gaps, like some missing words are there, and they try to guess that word. So that is how these pre-trained models are also trained, right? So here in a pipeline, we are suppose asking a task for fill mask, right? So there are some missing words, and in the next line, once we have the basically model, we can give a sentence with some missing word, and it can guess that word with some probability. So since we are giving top k is equal to 2, so we are asking for 2 guesses, and he said guess the words, right? So for example, this course will teach you all about models, right? So and the guesses are, it can be mathematical or computational, right? With some probability he has predicted. Or the next model is talking about question answering model. So basically here we are using the existing pre-trained model. We are not training as of now. Okay. So in case of question answering, we can ask for basically pass this task that we need a model for question answering to the pipeline, and we can ask a question and we can give a context. Now from that context, it can answer. Also, it can answer with some probability that what is the likelihood of that answer. Okay. So this is how we can out of the box utilize any pre-trained model using pipeline, and that also very easily, right, from Hugging Face. Now, if we go to the next slide, so as of now, we have utilized a pre-trained model. So obviously the pre-trained model can do good, but that's not the purpose, right? Because that is not specialized for any particular task. But in organizations or in real-time uses, right, we need models for very specific tasks. So for that, now we need to fine-tune that. So what is the meaning of fine-tuning? As you can see on the right-hand side, what is LLM fine-tuning? So we have the initial huge amount of corpus data through which the pre-trained model is trained. We call this pre-trained transformer model. So these models are transformer-based model in Hugging Face, right? Now, once we have the pre-trained model, then comes the fine-tuning. So this pre-trained model is good for the basic type of task, is good at the basic grammar, basic context, basic semantics or syntaxes. Now, if you want to use this particular model for a specific task like question answering, then now we have to fine-tune it for question answering. So for question answering, obviously, we have to fine-tune with lot of question answer pairs, right? For example, if we want to create a chatbot for a company, then in that case, for that context, we need the data now, question answer pairs. And with that set of question answer pair, we can fine-tune that pre-trained model so that that model will be suitable to answer with respect to those companies' context, right? Now, this is basically a specific model, right? So similarly, for different type of tasks, a pre-trained model can be used. There are different pre-trained models also for different types of tasks, and they need to be fine-tuned, right? Now, why fine-tuning? One of the basic reason of doing fine-tuning is because it's not always computationally feasible, and from complexity point of view also, it is not feasible to train something from scratch by everyone, right? It needs a lot of domain knowledge, computational complexities, all these things. But if we do just fine-tuning, then the thing becomes a bit more easier, and that can be accommodated by a mass amount of people, right? So that is the main reason of fine-tuning. The second reason is that's computational, right? We don't have the time to always actually train everything from the scratch. In that case, if we use fine-tuning, we can save a lot of time, right? And the computational complexities, and eventually carbon footprint, all these things, environmental things also get involved there. Okay. Now, okay. There are different types of fine-tuning that will come to know gradually, right? But there is a full fine-tuning where basically the entire LLMs can be fine-tuned, right? Basically the weights and biases of the entire framework. Also, there are partial fine-tuning where basically there are different analogy, right? We can take few layers, particular layers, we can fine-tune. And based on that, again, the complexity and the computation cost, everything gets involved there, okay? Now, going to the next slide. So now we have described about what is using the pre-trained model, what is the meaning of fine-tuning. Now, how we can do fine-tuning, we'll gradually try to understand that, right? So for that fine-tuning purpose, transformers actually provides a trainer API. So it's like an interface which these deep learning models like transformer deep learning models, they provide to fine-tune the transformer-based models, right? This is it's an interface, and it also basically abstracts a lot of complexities. Okay, so if there is a trainer class, within the trainer class, we can pass different parameters. We'll explain all these things later. We'll understand this in better later. But on a high level, what this trainer class does, actually, we can pass multiple parameters to the trainer class. Okay, like the evaluation metric, what are the hyperparameter, how you want to tune them, what is the model we are going to use, or our training data set, obviously training, validation, test data set, what is the tokenizer that we're going to use to tokenize the data, right? So all these informations, actually, we can pass through the trainer class or the trainer API, right? Using them, the trainer API can actually start doing the fine tuning. So we can give all the constraint to it, and then the trainer will do the training part. Okay. Okay, so now we will try to understand on a high level that what are the fine-tuning steps. So here we will get a better idea of what is a trainer class, right? So to start with the fine-tuning step, obviously you need further data, right? So we need a data and a base model, right? And then we'll try to fine-tune that model, right? With that data, because pre-trained model is obviously trained, and now we have some custom data that we want to retrain the model with. Okay, so here the data set that we are using is basically a review data set. So it's a customer review data set on different type of business customer interactions with the clients. So from the data set, so that is our training data set. Okay. And the model that we are going to use. Okay, so before that, we need to have a tokenizer, right? We need the tokenizer to process that text, because for any type of any training, right, first we need to pre-process that text. We need to tokenize. So what tokenizer we need to use? So the model that we will use here is basically a BART-based model. As we are using the BART-based model, so we use a tokenizer that is also BART-based tokenizer, right? So from transformer, we can import a tokenizer. It's called auto tokenizer, and we are actually using the BART-based cased tokenizer, right? So this tokenizer will be used to tokenize the basically the text input, right? So these are some basic syntax and semantics, right? Tokenizer, some padding and truncation. These are basic things, right? I mean, the standard things in machine learning pre-processing, we need to pass this, whether we need truncation or padding length, all these things we need to pass. Based on that, the tokenizer will tokenize the input, right? And give the basically the vector set. Also, there is a provision because sometimes the data sets can be huge, right? And if you don't want to use the entire data set to train on the first go, or based on the computational capacity that we have, right? Based on that, we can filter the data set. Like here, we can actually see, we can see that we can shuffle the data just to get a standard set of indexing, and then we are taking only the first 1,000, right? So in that way, there is a provision to take the number of data set we want to try the training with. Right. So in this slide, we can see that we have the data set, right? We have taken the data set. We have made a provision to tokenize the data set that is also using this BART-based model. And then we have basically taken few entries from the data set. Okay. Okay. Now, once we have the data, we need to look into the model, right? So for the model, what we are taking is, so there is a auto model for sequence classification class. Okay. What does it do basically? As the name suggests, right? Auto model for sequence classification. So it's a sequence classification task, and it can automatically choose the model. So for example, if I give a BART-based case, right? So internally, it will actually select a BART model. Okay. And the number of level is 5 means it was a review, right? So there are different basically categories, levels for that review. So we want 5 levels, right? So that's why we are talking about 5. The number of levels is equal to 5, right? So this is how we are basically, as of now, using the pre-trained model. So this is the pre-trained model, right? As of now, we are using we have taken the pre-trained model. Now, once we have the pre-trained model, we will now create the training arguments. So we need training arguments, right? For training, there can be a number of different arguments. As of now, we have taken very basic argument. This is the output directory. So basically, where this is where the output will be stored. Okay. We'll come to the other training arguments also as we proceed. But so the point is, we can have some sort of training arguments, right? So we have the base model, we have the training arguments. Now we need the evaluation metrics. For any training, we need the evaluation metrics, right? Just to track that how the training is going on, right? Whether it is overfitting or underfitting, all these things, right? So for that, we need that evaluation metrics. So so this trainer does not automatically have any evaluation capabilities. We need to pass evaluation parameters, right? So So it can be accuracy, it can be or custom evaluation function or method we can pass here. Or we can pass it as a strategy, basically, as you can see here, right? In the last line, we are saying that the set of training arguments are like we have the output directory, and we are passing evaluation strategies as epoch, right? So there can be different type of evaluation strategy also. And epoch basically necessarily means that at the end of every epoch, this will be evaluated. The model performance will be evaluated, right? So basically, as of now, we are creating the training arguments for the training. Okay. Okay, so now we have the training arguments ready for fine tuning. So this is the step for the fine tuning. So as we were discussing earlier, right, that the trainer class actually does a lot of complexities, and it makes the training process, fine tuning process very seamless. So here you can see we are basically instantiating a trainer class here, right? And within trainer class, we are passing all the required artifacts. Like we are passing the model. This model is actually the pre-trained model, right? Then we are passing the training argument. So whatever training arguments we collected, we are passing the training argument. We are passing the training data, evaluation data, right? So these will be used for the training and evaluation purposes. And also the computational metrics, compute metrics we are passing. So there can be many other training arguments that we can pass for any type of training. And once we have this trainer object, basically we instantiate this trainer class with all these parameters, right? Then we go for the actual training process or the fine tuning process for here, since we started with a pre-trained model, right? And how we can do that? So there's a simple step for that. Just we need to do trainer.train. So then once we do trainer.train, right, it will basically start the fine tuning process. Okay. Okay. So once that fine tuning process ends, actually based on the different criteria we set or evaluation metrics, right? So we get a model, right? And it's very important to save that model because we cannot afford to fine tune again and again, right? So we need to save that model. So for that, we have basically this save pre-trained function or method through which we can save a model. Okay. For example, here, like we have seen that we have started with, suppose, BERT based case model, right? That is our pre-trained model. And once we have fine-tuned after the training code, we can save the model as my BERT model, right? It's a custom model, right? So we can save that model. And going forward, once we need to use that custom model, we can just load that model, right? So from BERT model, we are loading from pre-trained, right? And we're giving our custom model rather than the standard model, rather than the pre-trained model. Right? So this is how we can save our fine-tuned model. And so as Vinita was discussing, right, that trainer, this Hugging Face is like a GitHub, right, for all these transformer-based models, like deep learning models, right? So it's a community, so we can fine tune, and there is a provision to contribute to the community also. So if you want to save the model to the community, right, post the model to the community. Maybe someone has trained a model, fine tuned a model for a specific task, and he want to add that to the community, right? So there is a provision to do that. So what we need to do that? So in the training argument, we need to basically set push to hub as true. And as the name suggests, right, this is going to push this model to hub, and we need to pass some authentication criteria also there, so that at the end of the training, we can push this model to the Hugging Face artifact, at the Hugging Face website, actually. Okay. So now we have basically on a very high level discussed that how or what a fine tuning means, like, okay, looks like, what are the steps we need to do. It can be a bit more complex, but we have explained a bit comparatively easier level, right? But it can be obviously complex when you actually end up getting a really effective fine-tuned model for your purpose. But what we try to capture are basically the steps that you need to go through step by step, right? Now, one thing that is very important is the optimization of your training, because as you all know, right, this fine-tuning or working with large language model is computationally very complex, very costly, actually, right? So we cannot afford to just keep on training, right? It will ask for a lot of time, lot of GPU memory, which is costly, right? So we have to come to a trade-off or proper set of optimization techniques so that the training is actually feasible, right? So there are different methods. We will explain them. For example, as you can see, right? This is for the first case, it's a vanilla training. So we'll start as we'll take it as a base case, right? So in the training argument, we are passing part device training batch size, okay, and default arguments. So basically, default arguments are like all the default set of arguments that is required. Along with that, we are adding a new parameter here, that is part device training batch size. What does that necessarily means? For example, whatever computational device you have, like for example, if we take GPU, if we have a number of GPUs, right? In each training iteration, in all the GPUs, suppose four mini batches will be basically loaded to process. Okay. Now we can okay. So if we have four number of suppose mini batches on all the computational devices, right? Now what is the time that is taking? So there are some basically analysis. So it's saying that for this task, it is taking around to complete for the training basically to get completed to over. It is taking around 57 seconds, and that amount of GPU that was occupied is around 14 GB. Right? It's close to 15 GB with this particular training argument set. Now, if we take some other parameter, for example, gradient accumulation. So what gradient accumulation is? Gradient accumulation is like this is a underlying neural network is working, right? So there will be backpropagation going on, and basically these parameters will be changed based on the gradients, right? So rather than doing that change every time after every iteration, we will wait for few steps. For example, here gradient accumulation step is 4. So we'll accumulate the gradient for 4 steps, 4 iteration. And after that only we will go for the parameter changes. Okay, there's a gradient accumulation. So if we do that, since we are not changing the this parameter every time, as you can see that it is actually the GPU utilization is going down. Right? We don't need that much of GPU right now, right? But what happened since we decrease the part device batch size, right? So training time got increased because now it is taking more basically batch size, right? Or there is another parameter, for example, gradient checkpointing. So in case of gradient checkpointing, what it does, this is also a memory overload technique, right? We are not saving the gradient in the forward pass of the neural network, right? When the training is happening, there are forward pass, backward pass. In the forward pass of this training, we are not basically saving the activation on every iteration, on every point, right? On every basically node, we are not saving the gradient, right? We are saving for few cases, like a bunch of instances we are saving, and those are called gradient checkpoints, right? On the checkpoints you say. And during the backpropagation, somehow based on those checkpoints values, so somehow we try to recalculate that what can be the values of those nodes which are not saved, right? So what it eventually will do is it will save a lot of time, a lot of basically memory, since you're not saving a lot of data, right? So GPU utilization, as you can see, is coming down, right? Initially, it started from around 15 GB, it came down to 8 GB, then it came down to close to 7 GB, right? But since we are recalculating again based on the checkpoints value, we will recalculate. So it will increase the training time, right? For example, as you can see, the training time is going high, right? So it's basically simulates an environment where we have limitations on the GPU, but we have flexibility in time. We can have a trade-off, right? So this is the main purpose of discussing these things, the training optimization, right? So based on the different use case, we have to come up with the proper value that suits the purpose. Right? Also, continuing to the optimization, there are different techniques. For example, this 16-bit floating point precision, right? So there are 16-bit, there are 32-bit. So if we go down to 16-bit from 32-bit, then it will actually increase the training speed, because calculation is going more fast. Rather than 32-bit precision, we are calculating in 16-bit, right? So calculation will go fast. So it, as you can see, right, the training time went down to 27 seconds. It's the same set of parameters actually. Like part device batch size is 4. As you can see the earlier slide, that with comparing to the vanilla training, right? The same part device batch size was 4. The training time was 57 seconds. GPU utilization was 15 GB. And the next case, we are adding just with that, what we are making changes, we are making the function, this floating point precision, actually, we are decreasing that. So here, as you can see, right, the GPU utilization is close to almost same, but the training time became almost half because it was very fast, right? And so what generally is does in practical. We combine all these things to come to a trade-off. For example, here, as you can see, there is a combination of all these things, which gave a decent, basically, combination of all those things, the time and the GPU utilization, the GPU requirement, basically, the GPU footprint, memory footprint, right, which is feasible for practical training. There are different other things also. One of them is like the different type of optimizer that we can use. It has been seen that if we use this ADA factor optimization, that eventually, again, offload some memory footprints. So as you can see here, along with that, if we the same set of parameters, basically, this combined and optimizer, if we add optimizer as ADA factor, then the GPU utilization even comes down more, right? And the training time is almost same, 50-56 seconds. So this is how we need to come to a trade-off. So this is a graphical representation of a different type of training optimization, how it happens, right? But this thing is very crucial when it comes to fine tuning, because this will directly, affect the training cost and time, right? Okay. So now I will hand over to Vinita again to start with another fine tuning technique, which is called PEPT. So yeah, over to Vinita.
Thank you, Shubhankar. So what exactly is PEFT? PEFT is parameter efficient fine tuning. Now, if you see, fine tuning all the model parameters is going to be very costly, okay? And it's not something which we want to do when we are actually fine tuning for our business purpose. Now, PEFT is actually a subset of fine tuning where it is a library for efficiently adapting large pre-trained models. So what exactly, like the name says, right? Rather than tuning all the parameters that is there in your pre-trained LLM, as you can see on the right side, right? We will just freeze the original weights. Whenever the first time when we are actually having the training, right? Those weights are frozen, and we will only select the ones which is required for our particular domain and add and fine tune those additional parameters. Okay. And then obviously only fine tune small set of the new parameters, which is cheap. Now, what happens because the number of parameters have now decreased drastically? There will be a significant decrease in the computational cost, storage cost. Also, it will yield performance comparable to a fully fine-tuned model. Okay. By freezing the early layers responsible for the fundamental language understanding, we preserve the core knowledge. So what happens? The LLMs that we have, that the pre-trained LLMs have a knowledge of everything. Like it's like a generic thing. Now we want to add something specific. Now, if we don't do this freezing of the original weights, right, and then training only for the ones which we need, there will be a catastrophic, forgetting. Like it will start hallucinating. It will lose context of what it was supposed to do in the beginning. It will lose all the context of what it had gained before, and will now only focus on this domain specific task. We don't want that to happen. And the experimental results demonstrate comparable performance to traditional fine-tuning process across various NLP tasks and data sets. So this is something which you can directly go if you want to fine-tune a smaller data sets. Now, if you see the process, right, remember we had given a high-level diagram of what happens when we train large language models. It's almost same. Like, we have data collection, pre-processing, then we have task-specific data sets, then we have parameter identification, like what all the parameters is have been trained for. And then from that, we get the subset selection of like which all should I, fine tune my LLM for my domain, and then go with the fine tuning process and back to evaluation. And then again, maybe if that is not the right thing, again, you'll go back, you'll check again, you'll get a new subset of parameters, assign them weights and train again and compare the results. So this is what PEFT is for. There is another one called as retrieval augmented generation, also known as RAG in common. Now, this is mainly used in conversational AI model where you combine retrieval and generation techniques. So the retriever component searches for the relevant information in a knowledge base. That is the vector database you see here, right? And the generator component uses the retrieved information to craft the response. Okay, so if you see the diagram there, right, how exactly it works. The user first submits a natural language question or query. That is the first thing that you see there. Now the framework, you see that the RAG framework that performs a semantic search of this vector database, which will have the original data as well as the new content. So why RAG is more important is it has a reliable source. Like, the more data you get on your domain, you keep adding that to your original content. So now you are training it only for, it already has a knowledge of what it's supposed to be. Plus it has now having a precise knowledge of what is a domain that you want it to be trained on. Okay. And the contextual results or answers that you get, right? Step number 3, you go and say that, okay, this is the data that I get. You give it back to the LLM, and LLM will rephrase it and give it as a response to the client. So the RAG model generally works by first using the LLM to understand what is the query that the client has given, then LLM uses this understanding to retrieve relevant information from the source or the database that you see. And then the LLM generates a response and give it back to the client. So this is how RAG works. And why we want to use RAG? Because it's, as I said, it is up to date with response, because you keep adding the new content which is only relevant for your domain. It avoid hallucinations because we are not doing any scrutinizing with original content. Also, there is high level of transparency and interpretability. So these are the two main ones. There are many more, but currently these two are used in a lot of like the use cases which I've discussed before, right? Now we have talked a lot about fine tuning, how to do it, what are the different techniques, what are the challenges and opportunities that fine tuning has. Okay, we'll start with the challenges. So the first thing is, many a times the main issue is there is data scarcity and domain mismatch. One particular data set cannot be used for the other domain directly. Okay, so there is very less data that you have, and you have to train it with that and still get the maximum or optimal output from that. The second, as we discussed, is catastrophic forgetting. Like, if you fine tune it too much, then there is a chances that it will forget what it was supposed to do. Like, it will lose that generic knowledge which it had. Overfitting. So overfitting is like this, you might have seen even in the generic AML, where you keep training it in such a way that when you actually take a subset of your training data set and try to get the output is perfect, but when you train it with a new data set, it was nowhere related to that. So it starts taking only whatever is in the training set and just give that. It has not been trained properly, it just memorizes the training set. So that is what overfitting is. Now, hyperparameter tuning, like I said, right, you need to pick up the best parameter, as in the best weights to them, and keep tuning it till you get the best output from the model, the LLM fine tuning model that you have generated. So the crux here is you have to figure out what are the parameters that is required and also assign the correct weight to them. Bias amplification, as we know that because we are feeding them with whatever data we have currently, right? So whatever bias is there in that, now that will get amplified if you don't train it in a proper way. There's a very high tendency that the bias that is mentioned in your training data set is going to get more amplified in such a way that there is one set which is working perfectly fine, and for the same thing the other set doesn't work. Now, what are the opportunities that you have? So, as I said, right, when we were discussing PEFT and RAG, there is significant performance results that we have seen when we use RAG or PEFT, different fine tuning techniques, right? It is faster and cheaper because you need less computational resources. You need less storage. So it is faster, it is cheaper, it has flexibility, it has domain adaptability, and also it has efficient resource utilization. Now, these are some of the reference pages that we have actually, had helped us in understanding or getting a better understanding of fine tuning. And yeah, any questions you have, we are open for Q&A. If you have any queries, you can reach to us in our LinkedIn profile. We have shared it here.
It was a really good session, Benita, Shubhankar. Thanks for it. I think there are two questions right now. So one is not a question actually. I think Silas had a technical issue on her side. She couldn't see the screen on the thing, but we could see it actually. I'm there on the other side. There's a question from Ashish Gupta, IBM. He's from IBM. Uh, Agent versus RAG, Hugging Face versus OpenAI. So I'm not sure what the question is about. Ashish, if you can be more clear on this. Agent versus RAG, Hugging Face, Face versus OpenAI is what he's written.
I think Hugging Face versus OpenAI, he's probably trying to figure out like what exactly, which one is better. Well, both of them are really good, but Hugging Face, because a lot of people are already contributing a lot to Hugging Face. There is, like I said, right, there is a plethora of models and uh, data sets, documentation, and they have it in like in a very what to say, like it's so sorted out that it's the best place you can go if you want to learn more and you want to train your model or to understand something which is specific to your domain, which works best, because a lot of people contribute to that. OpenAI is also an alternative uh, option that you have. uh, yeah, whichever, depending upon your domain, and if which one gives you the best model, best data sets, based on that probably you can go with one of them.
Uh, Thanks, Vanita. He also asks agent versus RAG.
Could you explain what exactly is
Yeah,
he trying to
in the
say?
same line, it says Hugging Face versus OpenAI and
Mm.
agent versus RAG. So I'm not sure what that is.
It will be better actually to get some more context on that.
Yes, yes.
But yeah,
Just
so
one.
RAG is the method, right, that we need to explain. It's for a very particular uh, I mean, work actually. Okay, it's close to fine tuning, but not exactly fine tuning. But that's a widely used in industry.
So we'll take a question from Dhananjay Pal. He's from Samsung Electronics. He says, if a model is pre-trained on a specific data like conversation models, and we need to enhance it for certain type of logs, what is the best approach for this?
Pretty much specific data like conversation model, you use it for a certain type of logs. What is the bill appropriate? So in general, like for example, yeah, there can be a pre-trained model, right? Which is good for some basic type of stuffs, but when you want to fine tune for some specific type of task, right? For example, I suppose you are doing something with respect to logs, right? So one thing that you need is you need to have a data set, right? Training data for your purpose. For example, if you are doing want to do specific type of work with log, you need to have some data set for that specific type, right? And on an example I can give you, for example, right, if you want to take some existing model, and what I want is uh, like I want some suppose I have taken a basic model, right? And on top I want to train fine tune it for some medical purpose type of conversation. Okay, so in that case what I need is I need that medical type of data, right? Or if I want to fine tune it like from a maybe from a excel spreadsheet, right? It can gist things to me, right? So in that case you need to fine tune with in such a way that you need the data, and that data knows, right? The data is like the input will be an Excel and the output will be what is the gist of that, right? So similar type of basically data set you need for any type of fine tuning. This is what
Yeah,
I can.
Dhananjay says I need to find out summary of a log.
Correct. Yeah. If you want to find out summary of a logs, right? In that case, you need to provide some sort of such data also, where you are basically summarizing from logs. So you can take any pre-trained model, right? And on top, you can fine tune it with such type of data sets, which actually summarize from logs, right? So that it will understand better actually that what exactly you want to do.
Yeah, thanks, Shubhankar. I think it answers Dhananjay's question. Moving on to Ankit Mishra from IBM Corporation. How can we learn AI ML? Anything you can suggest? I'm a platform engineer and want to learn. Uh,
So
that's
I
from
think
Ankit.
there will
Yes.
be yeah, a lot of study materials right now. It is online available, and just start with that. Not just going through books or like course material. Doing small implementation, I think, will really help.
Yeah, there is a lot of YouTube videos which are there nowadays, that even for Hugging Face, there are a lot of tutorial videos that is available. So maybe you can use that and get a good understanding of that.
Yes. Uh, so Ashish Gupta from IBM, who asked us about who asked us about the
Drag
comparison.
versus.
Yes, I was
Okay.
reading about RAG. That's what he says,
Yeah.
which helps
So
with real-time context.
basically, see,
Agent
you
also.
can actually use both of them, RAG as well as agent. But agent is kind of like a pretty slow one when compared to RAG with respect to the results that have been generated. But however, you can use a combination of RAG and agent for, you know, mm, that is also kind of okay. But well, we don't unless we understand which particular domain or what is your need, right? We can't suggest which is better, but in general we have seen that RAG is having a much more better performance when compared to agent.
Yes. Next question is from Dhananjay, again from Samsung Electronics. What should be the ratio of the custom data set?
Okay, so like there is no standard like answer to this. Rather, we should answer in a different way. For example, uh, is most of the cases what we have seen, right? Getting custom data or use specific data is actually very complex, right? So it's this is very rare case that we have lot of well prepared data, right? So first of all, that is a scarcity. Second is, if we have a good set of data, then what parameters we should consider is a evaluation metric, right? Whether you are doing overfitting or it is still underfitting the model or not. So those will basically are good indicators that whether you really need more data or not, or the data set that you have and that fine tune that you are doing or training you are doing, that is good enough or not, right? It's really hard to answer that what should be the ratio in that way.
Also, with whatever data set that you have, right? That is where we actually talk about this evaluation and validating that you have the right things. So that you have to keep continuing that process till you get that good data set. Unless you have a good data set, there is no point in fine tuning. So there is no particular ratio that you can do, but you can keep considering, like, what the data set I have, is it good? Can I do what sort of fine tuning mechanisms will help me out in this case? Also evaluate once you have picked your own the model or architecture that you wish, and basically keep evaluating till you have a good uh, output or the desirable output from whatever data set you have, whether it is giving the correct ones.
Right. Because while we are doing fine tuning, right, we need to keep one thing very clear, that we should not forget the pre-trained models capabilities, right? Because that is holding the strength of understanding basic language, right? Because if we fine tune it too much, what might happen? It might forget that information, right? Which is not good for us. So there should be a trade-off, like it holds the basic understanding good, which is the basic grammar, basic context, basic semantics, right? Because it was trained on huge amount of data. We can't any pre-trained model is trained on huge amount of data. So we should also consider, we should not forget that, just for the sake of fine tuning too much on our custom data.
Yeah. Thanks, Vinita. Thanks, Shubhankar. I think the audience can ask more questions they have on this session, and they can drop their questions on the box given below, and we will be answering them and posting it on the webpage, and they can refer, the answers there. Thanks again for the session. Kalyan, would you like to close this? Yes, I think we are close to the closing time. I'll kindly drop all the questions on the box, and we'll answer them. And we'll see you on the next session of SNEA India. And thanks for joining us today. Yes.
Thank you.
Thanks, Benita. Thanks, Shankar. Yes.
Thank you so much. Thanks everyone for joining.